Hi everyone, my name is Jakub Starun. This is the next episode of MedChem Essentials, scientific seminars devoted to medicinal chemistry. Today we continue talking about solubility, in particular strategies to improve solubility of our drug molecules. So we will see first general overview of different strategies to improve solubility, which will be divided into in particular insertion of hydrophilic or ionizable group. Then we'll discuss different ways how this affects solubility of addition or removal of hydrogen bonding, and finally disruption of molecular planarity. So all strategies to improve solubility can be categorized into decreasing hydrophobic properties or decreasing crystalline stability. And these ways could be divided into like insertion of hydrophilic or ionizable group, addition or removal of hydrogen bonding, designing a prodrug, bioisosterism, destruction of crystal packing, and miscellaneous ways like mixing one and another. This will be our model structure that will be used at the initial part of the presentation to exemplify these different ways to improve solubility. So if you are talking about insertion of a hydrophilic or ionizable group, we can, for instance, introduce a piperazine or some amide with hydroxyl group. If we are talking about addition or removal of hydrogen bonding, so if this molecule is not soluble enough, we can methylate hydrogen bond donor and thus remove hydrogen bond, which may potentially improve our solubility. Now, if we are talking about the prodrug, this can be introduced via a hydrolyzable, for example, ester bond. Now, when we are talking about bioisosteric replacement, this is based on the, for instance, introduction of the heteroatom into aromatic ring, or changing the aromatic ring, like benzene, into 5-membered heterocycle, which is more polar. If we are talking about disruption of molecular planarity symmetry, then we can most generally increase the sp3 fraction of our molecule through, for example, changing the benzene into cyclohexane, or introduction of the ortho substituent that will disrupt the planarity of the bi-aromatic biphenyl system. Now, let's see some examples that exemplify the insertion of hydrophilic or ionizable group on our model drug molecule. So this molecule is quite low soluble. If we introduce homopiperazine, we substantially increase solubility. For the introduction of the methylpiperazine, solubility is also increased even more than with the homopiperazine. And we have another strategy like removal of the hydrogen bond donor through the methylation of the distal nitrogen atom. The hydroxypyrrolidine is also quite nicely soluble, whereas the hydroxyazetidine is not that much soluble. So you see different hydrophilic groups or ionizable group to a different extent improve our solubility. And now we'll need to assess all of these different modifications in terms of the biological activity and other properties, and select the one that will be the best in terms of the overall properties. Now, when we are talking about addition or removal of hydrogen bonding, then in the case of thalidomide, if we methylate the hydrogen bond donor, the nitrogen, we see a 5-fold improvement of solubility. Of course, there is a caveat because this hydrogen bond donor, as in the case of thalidomide, is required for biological activity. So not always we can rely on the methylation of hydrogen bond donor, because we can just reduce and cancel our biological activity of the drug molecule. Very often, the hydrogen bond donors, hydrogen bonds, they are formed within the drug molecule as intramolecular hydrogen bonds. And now we'll see how this may potentially affect solubility. So on the following model molecules taken from this paper, we see how these intramolecular hydrogen bonds and how the nature of the hydrogen bonds affect solubility. In case of the change, when we have the dimethyl amide or monomethyl amide, the intramolecular hydrogen bond causes slight reduction, almost twofold, of solubility. Whereas here, the demethylation of this nitrogen causes substantial increase of solubility, possibly through the exposure. Like this molecule in general is more polar, less lipophilic. Now let's go to the benzimidazoles, and here the modification is either methylation of the nitrogen or introduction of the methylene group. So when the benzimidazole is methylated, there is no difference in terms of solubility between those two molecules. But if we have NH here, then the introduction or removal of the methylene group strongly affects solubility, because in the left-hand case, we have a strong intramolecular hydrogen bond which stabilizes this closed conformation, thus providing lower exposure to the hydrophilic environment of water and lower solubility. And here, this hydrogen bond is quite weak, so it facilitates an equilibrium of closed and open conformations of this molecule, which causes the exposure of these polar groups to the hydrophilic environment, thus improving solubility. And finally, for this aryl urea analogs, here again we have some intramolecular hydrogen bonds that not that much affect solubility. So this molecule is quite soluble. If we have dimethylated, this molecule is the least soluble. And if we remove the nitrogen, the aromatic nitrogen, both molecules are quite nicely soluble. So if we would be to summarize the impact of intramolecular hydrogen bonds on solubility, then assuming we want to improve solubility, improve the overall properties of our molecule, then we should choose either a strong hydrogen bond, which will facilitate open conformation accessible to water, or we should choose a relatively flexible and weak hydrogen bond, which will facilitate a continuum of open and closed states. Now let's talk about disruption of molecular planarity, symmetry, and crystal packing, and let's see some examples. So exchanging of this hydrogen into bromine causes substantial impact and improvement of solubility through the disruption of the planarity of these rings, because bromine is quite a large atom. If we introduce two fluorines, this is again exemplified by the dihedral angle, we see almost twofold improvement of solubility. And finally, we have a matching pair of this pyrrolidine and cyclopentane. The improvement of solubility is tremendous through the disruption of this of planarity and symmetry. This is a more planar molecule, and this is more 3D rich. So this is one of the disruption of this molecular planarity and symmetry is one of the most powerful strategy to improve solubility. With this, we've finished talking about solubility. And during the following presentations, we'll be talking about fractional bound in plasma protein binding. Thank you very much for listening, and see you next time. Bye-bye.